Ladies and gentlemen, class recording has started, hopefully with audio. So, last unit deals with forces and Newton's laws. So today, introduction to forces. 3 questions. What is a force? What does it do? What kind of forces are there? So let's start with the first question. What is a force? I'm assuming most of you have probably, used the term force before. If I ask you this question, you probably can come up with an answer. What is a force? At least as you understand it at this point in time. Good, Sam. Okay, pushing on an object. We can also do what to that object? Pull it, right? Okay, so a force is a push or a pull, which is fine. And that's what a force is. But in this unit, we're going to focus more on what force does. Suzanne, when you pull an object, what happens to it? It comes towards you, okay. What happens to it a lot of times as it's coming towards you? It was sitting there, right? Now it's coming towards you. In order to do that, what has to happen to its speed? It has to accelerate, right? If you push something, right? Same thing, okay? So, more importantly than what a force is what a force does. Forces cause acceleration. Forces are the cause of acceleration, meaning they cause things to do what? Speed up, slow down, or change directions, right? More generally, they cause things to change their, let's go with something else. Velocity, right? Velocity answers which question? What question does velocity answer? Remember our 4 questions?
What's the displacement and what direction it's going in?
Yes.
How much in which way?
How much in which way, or more
What it's doing?
right now, right? So forces cause things to change what they are doing at that very moment. And as we discussed a lot in the last unit, right, that means forces can cause objects to speed up, slow down, or change directions. Sometimes more than one of those at the same time. You can speed up and change directions at the same time. You can slow down and change directions at the same time. It's kind of hard to speed up and slow down at the same time. Yeah. Just know that more than one can happen at the same time. All right. So what is a force? Forces cause acceleration. Other things that we want to know about forces. First, forces are vector quantities, meaning they have to tell us what? How much in which way? In this case now, kind of the how much would be what? Like when we talk about velocity, the how much is how fast it's going, right? How much force, right? Or how hard are we pushing or pulling, right? So forces are vector quantities. They have magnitude, how big is the force, how hard are we pushing on that object or pulling, and then direction. Which way are we pushing or pulling? Because that makes a difference in whether the forces can cause something to speed up or slow down or change direction. So forces are vector quantities. They have magnitude, they have direction. How big or how much are we pushing or pulling? And then which way are we pushing or pulling? Because that causes, or that's important to describing what that force is going to do to the object. How will it cause it to accelerate? Good there? Next, I left a line out here, so you might have to draw it in. So, one of the things that we will do quite often in this unit is we will represent forces by arrows. Arrows are a good way for us to represent vector quantities because they have direction already built into them. So we will use arrows to represent forces, where the length of that arrow will, as close as we can, represent the magnitude, and then obviously the direction that the arrow points represents the direction. Because there is going to be times, not in the too distant future, where we are going to have to analyze a situation where there is more than one force. So sometimes if you have a force pulling one way and a force pulling the other way, the effect of those two forces might cancel each other out. One might partially cancel another one. You know, it all just depends on how that's the direction part. So we have to have some way to distinguish that direction. That's where the arrows come in. Good there. All right, two ways that forces work. The first way is generally what we probably think of as force most of the time, and we call that a contact force. Like its name suggests, right? We're going to change the motion of an object by physical contact. These are your pushes and your pulls and your hits and your throws and friction and stuff like that. Okay? These are probably what most people think of as forces. But in the last unit, we spent a lot of time talking about this, right? Ready? Is that acceleration? Absolutely, right? On the way up, it slows down. On the way down, it speeds up, right? Up at the very top, what does it do? Stops, but as it's stopping, what is it doing? Which way was it going before it stopped? Up, and now it's going, so it had to change directions, right? All three forms of acceleration in that trip, right? What force causes that acceleration? Gravity, right? I mean, we spent a lot of time talking about that and the effect of gravity and how much does it speed up and how much does it slow down, right? But because it's accelerating, it has to have a force. Gravity can change that object even though it's not actually touching it, right? There's no physical contact between gravity and that object, right? But acceleration still occurs. So the other kind of force that we have out there is called a field force, where the motion of an object is going to change even though there is no actual physical contact. Gravity is an example of that. But then throughout the year, we've talked about other kinds of field forces, right? Things like magnets and things like positive and negative charges. So magnetic force and electrostatic force. Something that goes along with that concept of a field force, and this doesn't show up in your outline, I added it this morning because I was looking at things we should know, and this is one of the things we should know, right? Is the force field. And we've talked about a field surrounding like a charged object or a field surrounding a magnet, right? It's an area where an object can affect another object by applying a force to it, right? So the force field is that area that surrounds an object that has a field force. We live in the Earth's gravitational field because we live in the area where Earth's gravity affects the motion of objects. Right? These magnets, right? That piece of metal at the bottom is in the magnetic field of this magnet because its motion is being affected by this magnet, right? The field is an area that surrounds an object where it can affect other objects. Now, if I put these too far apart, right, do they necessarily pull each other together? Or if I put this up here, does it lift up that other object? Right? Not necessarily, right? There's a couple of things that go along with that, a couple of factors, but what we find out is that that area that surrounds an object is stronger closer to the object, but weaker as you get farther away. So the field strength, or the ability of that object to, the ability of that object to affect other objects decreases as we get farther away. So the field strength decreases as we move farther away from that object. Good there. And like I said, we talked about that with currents flowing through wires, creating magnetic fields, and things of that nature. All right. Next. Now there's our contact force, right? That guy actually pushing it. Okay. Look at how much of a hoss this guy is. This guy with 4 lines of back force. Whoa. In case you believe they put.
That's you with your.
Yeah, that's what it is. So, I actually have a hard hat, so from
That's you pushing the scooter, right?
yeah, that's it. This is a preview of the scooter, the scooter lab right there. So Jordan, if that I don't know if that scares you off or not. I mean, if you want, I could only use like 3 lines of back force if it's too, it's just too much. So.
How is it that heavy? It's labeled fragile.
I mean, fragile things. I mean, they can be something big and fragile,
Ice.
right? Yeah. Have you ever seen a Christmas Story, right? Fragile, I mean, and then here, right? Field force at work, right? Here's a guy jumping off a cliff. I always tell myself when I show this picture that this guy is going to make it out far enough from the cliff that he's not going to hit these rocks when he gets to the bottom.
Looks like he's gonna die.
That's why I don't tell myself that, right? He's going to be fine. So,
Yeah, he just jumped.
So. All right.
He's now wonderful.
So, measuring force. Force cannot be measured in one step. There are several factors that go along with measuring force, or how much does an object change because of what we do to it. Therefore, the measurement for force is a derived unit, and that unit is called the Newton. You can probably guess where we got that. So, by definition, 1 Newton is the force required to cause an acceleration of 1 meter per second on a 1 kilogram object. We will review that when you guys get done writing it down. 1 Newton is the force required to cause an acceleration of 1 meter per second on a 1 kilogram object. All right, to illustrate that, let's take a look at this picture. So here's a picture of a hockey puck sitting on an air hockey table. So we're basically getting rid of friction so we can just focus on the hand pushing the object. All right, let's say, for argument's sake, that this hockey puck has a mass of 1 kilogram. Okay? It doesn't. Hockey pucks don't weigh that much, but let's say it does. Okay? And it says, that this 1 kilogram object has to undergo an acceleration of 1 meter per second squared. If we say that something is undergoing an acceleration of 1 meter per second squared, what does that mean? Acceleration of 1 meter per second squared means what? Mark, good.
The velocity changes by 1 meter per second.
For, in how long?
Oh, in 1 second.
In 1 second, right? So, if we were to push this hockey puck for a total of 1 second, right? If it started off at rest, right here, if it wasn't moving, after this 1 second, how fast would it be going? 1 meter per second, right? So we go from 0 meters per second to 1 meter per second, right? If we can do that to a 1 kilogram object, that's 1 Newton's worth of force, right? So taking this 1 kilogram object, making it go from 0 to 1 meter per second, over a time of 1 second, which isn't very fast, and it's not, and that's kind of a long time, right? If you think about pushing something for 1 second, right, it may not seem like much, but if you're continuously pushing 1,001, right? To get it to go 1 meter per second is not very hard. So a 1 Newton is not very much force. Okay? All right, good there. Okay. What we find out is in looking at nature and looking at how do things work, we find out that even though there are very different types of forces that we observe on our big level of peopleness, right? The macroscopic level. When we look at it on a microscopic level or even an atomic level, we find a lot of similarities. Now, this information is a little outdated. Your book is a little outdated, and some of these things have sort of been combined together. If you know anything about like string theory and things like that, some of these things are combined together. So this information is a little outdated, but go with me on it for here. Okay, go with me. All right, so first, out there in the universe, we find out that there are a limited number of types of forces. They get applied in different ways, but when we look at their nature, there's really only a couple types of forces. So first, electromagnetic forces. We've talked a lot about electromagnetic forces in this class. Electromagnetic forces exist between what? What parts of atoms? Nucleus and, I was looking for something a little smaller actually. Electrons and protons. And why electrons and protons? Because they have what? They have charges, right? So electromagnetic forces are those forces between charged particles, specifically positive and negative charges. Right? And we talked a lot about the idea that like charges will repel each other and opposite charges will attract each other, right? Electromagnetic forces are unique in the sense that they are the only forces that can both attract and repel. So electromagnetic forces. You find out that if you start looking at things like contact forces and like friction, at their core, they are really just electromagnetic forces. All right, let's breeze through these last parts here. Okay. So next, strong nuclear force. We talked about the strong nuclear force a lot when we were talking about radioactivity, right? The strong nuclear force acts where? On the nucleus. And why does the nucleus need a force acting on it?
Because there are protons in it, they repel.
Right, all those protons want to repel each other, right? So, force of attraction that acts on protons in the nucleus, pulling them together. There's a lot of evidence to suggest that neutrons play a role in that strong nuclear force. They're not the only thing, but there is some evidence to suggest that, right? Force, it's an attractive force that holds protons together in the nucleus. Why? Because by nature, protons want to repel each other, right? The strong nuclear force is very strong, but just like these magnets, the farther we move the magnet away from this piece of metal, the less force it can apply to that metal, right? So is the case with the strong nuclear force. It holds very, very strongly, but only over a very short distance, like the nucleus. Once you get outside the nucleus, you don't experience the strong nuclear force a whole lot, because it doesn't act anywhere outside the nucleus, right? It gets weak very quickly, but where it's strong, it's really strong. All right, next, weak nuclear force. Force of attraction that acts on all particles. What you find out is if you start looking at an atom, what you know about the way things move in the macroscopic world, that wouldn't work on an atomic level, right? Why don't the electrons just fly into the nucleus, right? There's some other things going on, right? Weak nuclear force is another attractive force that acts over the entire atom. And I said this is one of the outdated things. There really isn't a strong nuclear force and a weak nuclear force anymore. They've kind of been combined together. So let's just kind of gloss over this and move to the last one because it's pretty important. Gravity. There's a couple of things. And I don't know why, but gravity got labeled A next to it. It should be labeled D in the outline. See next to gravity there is an A, and it should be D. All right, what do we know about gravity? What does it do to things? What? It pulls them which way? Well, it's down here, but more specifically, or more generally, it's together, right? Gravity is an attractive force, right? Between any two masses in the universe. When you look at how strong gravity is, that was gonna All right, we'll finish this up on Tuesday, and then we'll start getting into Newton's first law and Newton's second law. If you have questions related to your lab report, email me over the weekend.